In this video, we will describe MAEEB tool, which performs the analysis of energy efficiency of pumping stations. To evaluate MAEEB potential, we will analyze a real pumping station composed of 4 pumps that pressurize an on-demand water distribution network. The manometric regulation established for this pumping station is 45 meters. In this case, all the pumps have the same size. They are INDAR 257 with 3 impellers each. One of them is activated with a variable speed drive and the other are fixed pumps. When the farmer demands some discharge, the variable speed pump starts working. When this discharge increases, the variable speed pump works in a higher frequency until it reaches the maximum. If farmers still continue demanding discharge, the first fixed pump is activated and the variable speed pump continues regulating the excess of discharge. We can calculate the efficiency of the whole pumping station with this equation that weight the efficiency of each pump compared with the total discharge. So we can see how the pumping station works when the demand increases. That is what MAEEB does, but considering many points in the working of the pumping station and considering the distribution of the demanded discharge along the irrigation season. The main limitations of MAEEB tool is that only permits evaluating pumping station with manometric regulation. Also, all the pumps should be equal. It doesn't allow to evaluate pumping station with different type of pumps. We are working in the development of other models that overcome these limitations. To start MAEEB tool, we just have to double click in this executable file. The first time it takes a little while to execute, and we start with the execution. So first we have to characterize the pumping station. We have to say the number of pumps and the head pressure of the manometric regulation. In this case, these are 4 pumps and with a manometric regulation of 45 meters. The second step is to select the type of pump. Type of pump that we have a database, and we select INDAR 257 with 3 impellers. All the pumps are equal. Here, the information included in this file is different points of the characteristic and efficiency curve, as we will see later. To generate the file that characterizes the pump of the pumping station, here we have the file, in this case INDAR 2057 with 3 impellers, and if we open that, we can see that we have a header with the discharge Q in liters per minute. The software is ready to work in liters per minute, not other unit, the manometric head in meters, and the efficiency. We can find this information in the manufacturer information, and we can see here the characteristic curve for the different pumps. In this case, BL 257 with 3 impellers is this one. So what we did is to, for each of the discharges, to calculate the head pressure. For 0 is around 118, something like that. For 2000 is 100, and so on. So the same we do it for the efficiency. This is the efficiency curve. So for 0 is 0 efficiency. We have here the scale. For 1000 we move to a 30% more or less of efficiency. So we take as many points as possible to characterize the curves, characteristic and efficiency curve, and we introduce that in the file that we show, this one. We load the information and we can draw the characteristic curve. It will take a little bit because it's calculating all the efficiency and working point. So we have here the characteristic curve QH and the efficiency curve Q efficiency and the working point. We can see here that the working point in this case is 5,912 liters per minute and the efficiency in the working point is 61.23. As we described before, it is important to know the distribution of the charges or frequency of the charges all along the irrigation season. For example, I will load, measure these charges in this water distribution network, and I will draw it. So we can check here that in X and Y axis the frequency of the charges and here the charges. This is the maximum discharge that appear actually in this pumping station, is less than 10,000 liters per minute, but we can see that the higher frequency of discharge are for low discharges, after medium discharges, and very low frequency of high discharges. So we have to know this distribution to weight the efficiency for each discharge in the pumping station. If we don't know this information, it is actually hard to take. We can analyze different type of statistical distribution. Based on our experience, we fit it to different Poisson distribution. For example, the A in blue, the B in red, the C in green, the D in black, and in yellow is a random distribution. So if we have a total on-demand irrigation network, we will see that the distribution of low discharges is much higher and the higher discharge is lower. If we have a rotational scheduled water distribution networks, we have the higher frequency of medium and high discharges. So depending on the demand of our network, we will select Poisson A, B, C, or D, or just a random generation. The random doesn't work well actually. So for example, we can select Poisson E, A. After that, we have to select the type of regulation. We can use one variable speed pump and fixed pumps the remainder, or two variable speed pump activated sequentially or simultaneously. So in this case, it's just one variable speed pump and fix the remainder. We can calculate the efficiency curve. As you can see in this plot, we have the efficiency of the whole pumping station for each value of the discharge of the pumping station. For example, if we stay here, we have for 2,473 liters per minute an efficiency of 71.11%. If we increase the discharge in 9,887, we have an efficiency of 67.23. So we have all the values of discharges and efficiency of the pumping station. With this curve together with the distribution of frequency of discharges of the irrigation network, we can calculate an average efficiency of the pumping station and an average absorbed power that gives us an idea about the global efficiency of the pumping station in its real performance. We can activate the other two options, two variable speed pumps activated simultaneously and the other two fixed pumps, or two variable speed pumps activated sequentially and the other two fixed pumps. The difference between these two options is that the one that works simultaneously, both of them are working on with the same frequency, supplying half of the discharge each one. And this one, what makes is that the second variable speed pump is activated when the decrease of the efficiency is high. For example, here we start growing the efficiency, but here it decreases. Before it decreases, we activate a second variable speed pump. We can check that with the curve, the green curve. You can see that goes up until this point in which the second variable speed pump activated and the efficiency gets much higher than with just one variable speed pump. So the fixed pump and then second fixed pump. So we can increase the energy efficiency of the pumping station for these discharges. However, if we use two variable speed pump activities simultaneously, this is the red line, you can see that the efficiency is much lower for low discharges, and after that it gets the same than sequentially activated variable speed pumps. But here we have low efficiency for low discharges. We have to remember that the frequency of low discharges is really high in on-demand irrigation network, so activating simultaneously two variable speed pumps is not the best solution. The best solution is activating them in a sequential order. So in the next and last step, we can check the average efficiency with each type of regulation: one variable speed pump, two variable speed pumps activated simultaneously, and three variable speed pumps activated sequentially. Also the absorbed power. Here we have the plot of the average efficiency and absorb, average absorbed power, but here have the numbers. So with regulation 1, the average efficiency is 67.6, with simultaneously two pumps, variable speed pumps working simultaneously 62.4, 5 points less. But with the two variable speed pumps activated sequentially, we have a notable increase in efficiency. That means that the average absorbed power is much lower than with one variable speed pump. So including or installing two variable speed pumps activated sequentially can improve the efficiency of our pumping station. Once we have evaluated the energy efficiency of the pumping station with the current manometric regulation at 45 meters, with MAEEB tool we can evaluate what happens if we change the pressure head, for example. What about if instead of 45 meters is 40 meters? We have again to click on load and drop the characteristic curve. And in this characteristic curve, we can see that the efficiency got worse, 55 over the 61 that we have with 45. So we click on next, we can check the efficiency curves and recalculate for the new head pressure and evaluate these new numbers. This is a really high potentiality of this tool to evaluate what is the best head pressure for a manometric regulation in pumping stations.